Assalamu alaikum guys. In our previous lecture we discussed about the equation of continuity. In this lecture we will talk about the Bernoulli's equation, which is very basic and fundamental equation of the fluid dynamics. It is the equation which relates the pressure of the fluid with its velocity and height in pipe of varying cross-sectional area. Without wasting our time, I will come toward the derivation. Before derivating the Bernoulli's equation, we have some assumptions which I have already written. The assumption number one, fluid is incompressible, and the fluid is non-viscous, and the third one is flow is laminar, that the liquid flowing in the pipe is with the laminar flow. Now coming toward the diagram, we have a pipe with varying cross-sectional area, and I have chose two ends, upper end and the lower end. The upper end has pressure P1 at its opening, and the displacement of the liquid in time t is delta x1, and the height at this point is h1 from our reference point. If we come toward the lower end, here the pressure is P2, the cross-sectional area here is A2, and the displacement of the liquid or fluid is delta x2, and the height is h2. The basic principle of derivation of the Bernoulli's equation is that the work done on the liquid is equal to the change in its kinetic energy and the gravitational potential energy. So we will start from the work. First I will find the work done on the liquid at the upper end. We all are familiar with the definition of the work. For the upper end, I will say W1 is equal to F dot D. Here the displacement is delta x1 as shown in the figure, and the force in terms of pressure and area is equal to P1 A1. For your facility, I will mention here that pressure is equal to force per unit area, hence F is equal to PA, and we put this value here. P1 A1 delta x. Similarly for the lower end, the work done W2 is equal to P2 A2 delta x2, but here we introduce the minus sign. This is because at the upper end the pressure is along the motion of the liquid, but here the pressure is against the motion of the liquid. In other words, work is done against the energy of the fluid. If we want to find the total work, that is W, it would be equal to W1 plus W2, hence the result will be P1 A1 delta x1 minus P2 A2 delta x2. As in our previous derivation, we assume that S is equal to V2. It is very fundamental equation of the physics. From here we can find distance from velocity and the time. Using this equation, we can find the value of delta x1 and delta x2. If the velocity of the fluid at upper end is v1 and at lower one end is v2, then this delta x2 for time would be equal to delta x2 would be equal to v2t v2t, and at upper end the displacement would be equal to v1t. Put these values in above equation. I am showing it with the arrow. Then net work would be equal to P1 A1 V1 T minus P2 A2 V2 into T. From equation of continuity, we all know that A1 V1 is equal to A2 V2. This is equation of continuity, and if they both are equal, we can assume them equal to other value that we may say AV. Put this value in the above equation, we will get W is equal to A V T into P1 minus P2. Dimensionally, we can prove that AVT is equal to the volume. How it may be proven? What is the unit of the area? That is meter square, and here is meter per second into second. Second will cancel out second, and this will become meter cube, which is the unit of the volume. So we can write here volume into P1 minus P2, and we can write that volume is equal to mass by density. So the above equation will get this form. Half of the derivation is almost completed. Now we will take account about the kinetic energy and the potential energy. So if we want to find the change in the potential energy, if we want to find the change in potential energy, that would be equal to change in potential energy mgh2, the final energy, minus mgh1, the initial energy. Similarly, for the kinetic energy, the final kinetic energy will be equal to the final kinetic energy minus the initial kinetic energy. Sorry, it's not the final kinetic energy, it's the net kinetic energy. Previously we have found that W is equal to mass by rho into P1 minus P2. If we apply the law of conservation of energy in these three equations, this will get the form this equation. And when we rearrange this equation, we get the equation of this form. This is the final Bernoulli's equation, and is also usually denoted by P plus 1 over 2 rho V square plus rho G H is equal to constant. Students, this equation is very important as far as exam point of view, and also in the fluid dynamics. It is used in aerodynamics, like in designing of the jets, aeroplanes. We will discuss its application in next lecture, that are in your book, Torricelli theorem, the Venturi relation. So goodbye till next video.